Good morning, Year 12 further mathematicians. 2 sub-chapters left of Chapter 11 to do with integration. This one is a continuation of something back in Chapter 9, I think, the differentiation chapter. We have to solve differential equations. Back in that differentiation chapter, we generated them, we wrote them out, but we didn't do anything with them. And it's because the method to actually solve differential equations is integration. So we're going to find the general solution of a differential equation today. Just a quick reminder of what a differential equation is. So it is an equation containing some derivatives. So dy by dx is, say, dy by dt's, could be different letters, dA by dv, etc. It's going to just contain a dy by dx. Now the key thing with differential equations is the solution to differential equations isn't a number. So when we've solved sort of linear equations, we'd get an answer x equals. If you solve a quadratic, you might get 2 answers. If you solve some trig stuff, you can get infinite answers, but all numbers. But solving a differential equation, the actual answer is a curve or another function. Okay, so is a curve. So the solution is actually a curve, or curves I should say. There's so many different types of differential equation, and we only have to solve one type at a single maths A level, and it's the type which looks like this. So we've got an equation, there's an equal sign, we have a dy by dx, and then we have some algebra. Okay, that algebra, f of x, g of y, is just the product of 2 functions. One function just containing x's, and another function just containing y's. Obviously, if we had dv's and dt's, it'd be function of v and function of t. But just 2 different letters, 2 different functions, one for each letter. Okay, this is called a separable differential equation. Okay, so this is called separable. That's the only type of differential equation you have to solve in the single maths A level. Now, there is a specific method on how you solve them. The clue is in the name. They are called separable differential equations. So you separate the letters so they are just x's on one side and just y's on the other side. But you've got to be very specific on which side you take stuff to. So I'm going to just separate this and take the y's to the left. So when I divide by g of y, whatever that function might be, I would get 1 over g of y, dy by dx, is equal to f of x. And then you do something very clever. Okay? You integrate both sides with respect to x. Integrate both sides with respect to x. Now let's see what that would do. This right hand side, integrate f of x with respect to x, that makes sense. This left hand side, maybe not so much, because you've got something to do with y's. How can you integrate that with respect to x if it's all y's in there? And it's because they cancel. And you're just left with integrating something with respect to y. Okay, this is the key step. You separate the variables and then you integrate with respect to y. Sorry, with respect to x in this case. And that's pretty much it. Okay, so then you do the dot dot dot. And that'll be it. So that method is take the y's to the left, x's to the right, and that's called separating the variables. Step 2, integrate both sides with respect to x. And then step 3, solve from there. Okay. The solution you get when you do step 3 is called the general solution. Okay, the general solution. And today we'll be finding these general solutions. And these solutions will be, if I did draw them out, to be curves. It'd be more than one curve, it'd actually be an infinite amount of curves. And that's got just all summarized into this general solution. Okay, we're going to move on to what an actual example would look like. E.g. number 1, we're going to find the general solution to this differential equation. We've got 1 plus x squared dy by dx equals x tan y. And this is a separable differential equation. You can use division or multiplication or wherever it might be to take all of the x's to one side and take all of the y's to the other side. So based on the steps from before, I would like to take the y's to the left and the x's to the right, using just division and multiplication. So I have to divide by tan y, so that would be 1 over tan y dy by dx, and I'd have to divide by 1 plus x squared, x over 1 plus x squared. And now I've got a function on the left just containing y's and a function on the right just containing x's. I don't really like the look of 1 over tan y, so I'm going to rewrite that as cot y dy by dx. So that's the first step, separating the variables. Okay, so step 1, separating x's and y's, that is done. Step 2 is integrate both sides with respect to x. Integrate both sides with respect to x. And the reason you do that is because these cancel. Cot y. Any ideas on what cot y integrates to with respect to y? Now this is one of the, I believe one of the standard ones you need to know. I think, or at least it's given in the formula booklet. So I'm just going to check to see in the formula booklet what this is equal to. If not, then we're going to be in a little bit of trouble. So I'm not seeing it. Okay. Pretty sure cot y integrated is in the formula booklet, but if it wasn't, this is the following way you'd have to do it. You'd have to remind yourself that this is integrating, cot is actually cos over sine dy, and leave that as it is for now, dx. Now you are, in the previous bit, we talked about integration techniques and we summarized everything that we had done before, from standard integrations you should know all the way up to integration by parts and partial fractions and everything. And both of these are examples of pattern spotting. Okay, the pattern which you need to spot with this is the following: integrating f dashed of x over f of x dx. All of these are connected to this pattern, and when you know that, then your guess would always be ln of the denominator. Okay, so let's try the guess for this side. I'm going to use a different letter to y for this. I'll use just z. So we're going to guess, we'll try z equals sine y. See how bad this guess is going to be. Sorry, ln sine y. See how bad this guess is going to be. dz by dy would be 1 over. But then you've got to times by sine y differentiated. What does sine y differentiate to? Well, sine goes to cos. Like so. And that is a perfect guess, actually. So ln sine y would be that thing integrated. I'm pretty sure this is in the formula booklet, so you wouldn't need to do this. But I can't find it at the moment in the formula booklet. Next one, again, follows exactly the same pattern. F of x on the bottom, f dash of x on the top. So my guess would be ln of the denominator. So I'll say y is equal to ln 1 plus x squared. dy by dx, see how bad the guess is. It's always 1 over. But remember to times by that thing differentiated, which is 2x. So 2x over 1 plus x squared. So almost just out by a factor of 2. So if I went back now to this, just call that step star, back to star. That thing, my guess was ln sine y is equal to integrating this, it was half of my guess, half of ln 1 plus x squared, like so. And then this would almost be it, okay? However, when you integrate, you need to remember the plus c. But I've integrated like both sides, but I don't need 2 plus c's. Okay, I just need one of them. As long as I put one of them in on either side, I'm going to put it on this side, plus c, that will actually count for both. Because if I had a plus c on this side and a plus d, say, on the other side, I could just take them to one side and they combine as one constant anyway. So you just have to remember the plus c on one side. Only needed on one side. And that would be it. Okay, this is called the general solution. This would work for every single value of c. So there'd be an infinite amount of these. And if I drew them on a sketch, I have no idea how to draw this. It's too complicated, but that would be it. Okay, and that is it. So general solution, I can stop there. They haven't asked for a specific form, so I can stop there and get all of the marks up to that point. Right. Things I want you to try yourselves in the textbook. So we are trying to find exercise 11J, which is on page 324, and you're going to try just question 1 and question 5. Question 1 and question 5, and that's it. Again, post your pictures of your workings on the class notebook, and if you've got any questions, let me know in the Teams chat and I'll help you go through whatever you need to. That's it. Enjoy the rest of your day.